A cosmic ray particle is moving in a straight path vertically down, and then it enters a magnetic field region. When it enters the magnetic field region, it starts following a curved path, a circular path. The diameter of this circular path is given. The particle's electric charge and its mass are also given. We'd like to find the speed of this particle, also given the magnetic field strength in this magnetic field region. Note that we don't know the sign of the particle's electric charge. We will determine that based on the direction of the circular path's curvature. The fact that the particle is following a curved path means that it is accelerating. Now, here we have a circular path. That means we will have an acceleration vector pointing towards the center of the circular path. That's the radial acceleration. Now, if we have acceleration, that means we have net force because acceleration comes from the net force, right? And where does that net force come from? That net force comes from the magnetic field creating a magnetic force, applying a magnetic force on our particle. So, well, are there other forces? Of course, there's gravitational force, but we will see later in the problem that we can ignore the gravitational force here because it's much smaller than the magnetic force. So the only significant force that's acting on this particle right now is the magnetic force. And that magnetic force is the net force, and by Newton's second law, that net force is going to be equal to mass times acceleration. Acceleration being the radial acceleration, acceleration of a particle moving in uniform circular motion. So let's set up our equation for Newton's second law. Let's set up our force equation that summarizes all that. Here we're applying Newton's second law. Net force equals mass times acceleration, and the only force we have is the magnetic force, so the net force is equal to the magnetic force. And the formula for magnetic force is Q times V cross B, Q being the charge of the particle, V is the particle's velocity vector, and B is the magnetic field vector. Now, let's take a look at the picture. I have shown here the velocity vector when the particle is at the bottom of the circular path. So velocity vector is always tangent to a particle's path. So then in this case, the velocity vector is horizontal, it's pointing right. Now, um, because this is magnetic force, and magnetic force is defined as the cross product of V and B at times the charge, um, its direction has to be perpendicular to the plane defined by vectors v and b. What does that mean? That means the force vector has to be perpendicular to both the velocity and the magnetic field vectors at the same time. So then the force vector is perpendicular to the velocity vector. And because this is circular motion, the force vector also needs to point inward towards the center of the circle, right? So in circular motion, force, net force, or acceleration don't have to be perpendicular to the velocity vector necessarily. However, because this is magnetic force, it has to be perpendicular to the velocity vector, and because this is circular motion, the acceleration and the force vector have to point inward towards the center of the circular path. And the force and acceleration could be like inward but not exactly perpendicular. When they are perpendicular, the speed of the particle will not change, only its direction will change. So that's the idea. And we set the magnetic force equal to mass times acceleration. So here, this is Newton's second law, the general statement. It's a vector equation. So the second equation is magnetic force equals mass times acceleration. Again, this is a vector equation. Now the third one is a magnitude equation. So I'm keeping everything positive here. I know that my magnetic force and my acceleration point in the same direction. So I'm keeping everything positive. That's why I have absolute value signs around the electric charge. So in the next line, let's substitute the given values and isolate our unknown quantity. That's the velocity or the speed actually of the particle. Here I have substituted the values. The particle's charge is 3 times the elementary charge. The angle between the velocity and the magnetic field vectors is 90 degrees, so theta is 90. And the particle's mass is equal to 12 times the proton's mass. Finally, r is not given in this problem, but d, the diameter, is given, so I put d over 2 for r. Now we see that actually I have v on the left hand side and then v squared on the right hand side, so these simplify. Let's rearrange this equation and isolate our unknown v, and also let's keep in mind that sine 90 is equal to 1. After rearranging our equation, we get v equals d times e times b, d being the diameter of the circular path, e is the elementary charge, b is the magnetic field strength, divided by 8 times the proton's mass. Now, is the particle positively charged or negatively charged? To find that out, let's apply the right-hand rule. Let's do V cross B. Align your right hand in the direction of V, which is horizontally pointing to the right, and then curl your fingers, right hand fingers, in the direction of B, magnetic field, that's the direction out of the page towards you. Your thumb will be pointing vertically down. So that would be the direction of the magnetic force if the particle was positively charged. But the force is pointing vertically up because it has to be pointing towards the center of the circular path, right? So because we have the negative direction, that means our particle is actually negatively charged. So the sign of our particle's electric charge is negative. The next question is it safe to ignore the gravitational force when we apply Newton's second law? To figure that out, let's actually calculate the numerical value of the magnetic force given that the diameter of the circular path is 1.1 meter and the magnetic field strength is 0.28 Tesla. And then we'll calculate the magnitude of the gravitational force and compare the two. After the numerical substitution, we get 4.9 times 10 to the negative 13th newtons for the magnetic force magnitude. Now let's calculate the magnitude of the gravitational force acting on this cosmic ray particle. Formula for the gravitational force is simply mass times gravitational acceleration. When we plug in the numerical values, we get 2.0 times 10 to the negative 25th newtons for the gravitational force magnitude. Now, this is much smaller than the magnetic force magnitude. It's actually 12 orders of magnitude smaller than the magnetic force magnitude. 12 orders of magnitude means 10 to the 12th power. In other words, the gravitational force is a million times a million smaller than the magnetic force acting on this particle. How does the speed of the particle change as it goes through the circular path and exits the magnetic field region? Well, the speed doesn't change because at any given time the force vector is perpendicular to the velocity vector, and consequently the acceleration vector is perpendicular to the velocity vector. An acceleration vector that's perpendicular to a velocity vector can only change the direction of the motion, but it cannot change the speed. In order to change the speed, you need an acceleration component that's either parallel or anti-parallel to the velocity vector, which we don't have here. The entire acceleration vector is perpendicular to the velocity vector. Hence, the speed doesn't change, but only the direction changes, and this is basically why we have uniform circular motion, meaning circular motion at constant speed.